In section 6.2, we already saw how to project a vector onto the subspace spanned by one other vector, but in section 6.3 we're going to look at orthogonal projections onto a subspace spanned by more than one vector. So here when we project onto a subspace, we again need an orthogonal basis composed of vectors u1 through up, and this forms an orthogonal basis for subspace W of Rn. Now every vector y in Rn can be written as y equals y hat plus z, where z is in the orthogonal complement of W and y is in W. So remember that y hat is a linear combination of the vectors u1 through up. This is a value that we've already seen in the past. But we add in the other projections and we get y plus up, y dotted with up over up dot up, all times up. And again, it is clear that we have a bunch of scalars and vectors, u1 and up, which form the linear combination, which is y hat. So let's look at an example, but before we do that, let's also note that z is equal to y minus the orthogonal component y hat. So if I take the two vectors y hat and z and add them together, I'm going to get the following. So this is, say, y, and y hat is in our subspace W, and then z right here is orthogonal to every vector in the subspace, so it's also orthogonal to y, and that's the vector z. So this is just rewriting this in a funny way, so we have y is equal to y hat plus z. So those two definitions for z are equivalent. So let's take a look at an example. Here we want to find the closest point to y in the subspace W, which is spanned by v1 and v2. And then we want to identify the distance of the point that we've just found from the vector y. So let's note that we have an orthogonal basis, v1 and v2, which span W. So 1 times -1 is -1, plus 3 is 2, minus 2 is 0. So this is in fact an orthogonal basis, and the rest of the problem makes sense. We cannot do orthogonal projections if we do not have an orthogonal basis to begin with. So let's do the basis, let's do the projection. So we have y hat, using the definition we saw before, and this is our linear combination. So we can go through the numbers. This is -1 plus 4 plus 3 is 6 over v1 dot v1, which is 3. So that fraction is 2, but we're multiplying by v1. And we add in the other vector, which is y dot v2 over v2 dot v2 times v2. So this is 1 plus 12 minus 6 is 7 over v2 dot v2, which is 1 plus 9 plus 4 is 14. So that fraction is 1/2, but we're multiplying by the vector -1, 3, -2. So let's add these vectors together. We get 2 plus 1/2 times -1 is 1.5. Then we have 2 plus 1/2 times 3 is 3.5. And 2 minus 1 is just 1. So that's our vector y hat. So let's sketch what we just found. we are dropping a vertical from y down to v1 and v2. Remember that this vector is perpendicular to every vector. This vector that we just drew is perpendicular to every vector in w. So it's perpendicular to v1 and v2. That means that the vector that we just found, which is contained in w, which is y hat, that's this vector right here. Notice that this must be the closest point to y, the closest point in w to y, because this is where it's perpendicular. We drop a straight line down to w from y, and that's got to be the closest point. If I were to slide out this way, obviously this leg right here would be longer than this perpendicular line here. So this is the shortest point, or the shortest distance between these two. So the point closest to y in the subspace w is this point here. Then we want to know how far this point is from y. So all we have to do is find the magnitude of z. We can solve for z in this equation. That is equal to the vector y minus y hat. But we know what y and y hat are. Y is the vector -1, 4, 3 minus the vector y hat, which is 1.5, 3.5, and 1. So when we do this subtraction, we get -2.5, 0.5, and 2. That's the vector z. The magnitude of z is the distance from the tip of y hat to the tip of the vector y. So now we want to find the magnitude of the vector z, that is the length of the vector z, and that's equal to the sum of the square root of the sum of the components squared. So that's 25 over 4 plus 1/4 plus 4, or 26 over 4 plus 4. So this will come out to the square root of 10.5. And this is approximately equal to 3.24. So that tells us that the distance from y, the vector y, to w, the subspace w, is 3.24. That's the shortest distance between those two objects. So now let's look at a second example. Here we have our subspace w spanned by these two vectors, and we have our vector y, which we would like to express as the sum of a vector in the subspace of w and a vector that is orthogonal to w. Notice that that vector orthogonal to w is going to be the vector z, and the vector which is in w is the vector y hat, which we will compute through an orthogonal projection. So this one is in w, and this one is in w perp. We need to verify that this is in fact an orthogonal basis, so we check the dot product between these two. So let's denote this as v1 and this as v2, and we check, does v1 dot v2 equals 0? And we check 5 plus 3 minus 8 is in fact 0. So that's a check mark there, and we can proceed with the problem. So first we'd like to find y hat. We have an equation for that from the orthogonal projection. So let's decompose this vector into its orthogonal components relative to w. So we have y is equal to, or this is y hat, is equal to So let's check this out. We get 1 plus 9 minus 10, which is 0, multiplied by the vector v1, plus, and what's y here? So y dot v2 is 5 plus 3, that's 8, plus 20 is 28, over v2 dot v2, which is 25, plus 1 is 26, plus 16 is 42, times the vector v2. So that is 4 over 6, or 2/3. We can just simplify that fraction. And so y hat is the vector 10/3, 2/3, and 8/3. But now we can find what z is, because we know what z is once we have y and y hat. So z is equal to y minus y hat. So that is the vector 1, 3, 5 minus the vector 10/3, 2/3, and 8/3. So here we get the vector negative 7/3, 7/3, and 7/3. Another way to write this would be 7/3 times the vector negative 1, 1, 1, and that's our vector z. So we have written y as the sum of two vectors, y hat and z, where z is the vector 7/3 times negative 1, 1, 1, and y is the vector, or y hat is the vector 10/3, 2/3, 8/3. So now let's take a look at theorem 10. Theorem 10 says that we have an orthonormal basis for subspace W in Rn. Notice that now we are no longer just working with an orthogonal basis, but we have an orthonormal basis. That means that all the vectors are unit vectors. That means that everything has length 1. If this is the case, if we have this condition where we have an orthonormal basis, then something peculiar happens. Then we can write the projection of a vector y onto W is equal to, so this is just from the orthogonal projections that we saw before. Notice though that this is equal to 1, this denominator. And this denominator is now also equal to 1 because this is an orthonormal basis. And this is also equal to 1, again because this is an orthonormal basis. This means that we can simplify to y dot u1 times u. So this is a scalar multiplied by the vector u1, plus all the other vectors in between, plus finally the vector y dot up times up. Again, this portion is a scalar, and this portion is a vector. So again, we have a linear combination of the vectors u1 through up. and this is the vector y hat. Now we will use capital U to denote the matrix formed with column vectors u1, u2, and so on through up. If this is the case, then the projection of a vector y onto the subspace W spanned by the vectors u1 through up, where u1 through up forms an orthonormal basis, is now u times u transpose times y. This is a very nice expression. Let's see where it comes from. So let's first write u times u transpose times y, and let's look at this first part. So this is u times the matrix u transpose times y. Now these are the rows u1, a row u2, so on through up. Take the transpose of all of those rows, of all those columns to get the rows, and we multiply by the vector y. What happens? So when we carry out this multiplication, we get u times the vector multiplied, this vector of u transpose vectors multiplied by the vector y. What happens when we multiply these together? I'm going to get y times u1 transpose. That's the row. That's just dotted. That's just dotting y and u1. Same thing here, I'm just dotting u2 and y through up and y. Now when I multiply this out, this is the column vectors u1 through up multiplied by this vector of entries. Now this is just a vector of numbers. So when we multiply this out, we get u1 times the scalar u1 dotted with y plus all the other vectors in between times up, the vector, times the scalar up dot y. And this is exactly what we had before. This is the projection of y onto the subspace spanned by W, or the subspace W spanned by all the u vectors. So this is y hat, or the projection of y onto W. So this is why orthonormal bases are even better than orthogonal bases. So that concludes this video.